Hi all. So welcome back to discussion on the theory of scattering. So today we are going to discuss the scattering of spinless particle. Okay. So before going to the detailed discussion on the scattering of spinless particles, so we would like to uh, take certain assumptions to simplify our studies. Okay. So these are the assumptions that we are going to make. Okay, so the first assumption, since we are studying about the spinless particle, so we can assume that so both the incident particle and target particle have no spin. Okay, so both incident and target particle have no spin. Okay, so this is a very simple assumption. Okay, now the second thing is we assume the scattering is elastic. So assume scattering is elastic. So elastic means the incident particle and scattered particle will have same kinetic energy. That is, the kinetic energy of the incident particle is not lost. Okay, so that means the kinetic energy of incident and scattered particles are same. So if that is the case, then the kinetic energy of the incident particle may not be used to change the internal structure of the target particle. So in other words, we can say that the elastic scattering means we are not considering the internal structure of the target particle. Okay, so that means there is no change in the internal structure target particle during the process. So the internal structure of the target particle remains unaffected in the scattering, in the elastic scattering. Okay. Now the third assumption is the target particle is very thin, so therefore there will not be any multiple scattering. Okay. So assume target is very thin. So therefore an incident particle will interact with only one target particle. So which implies no multiple scattering. Okay. And fourth assumption is there is no coherence between the scattering particles. Okay, there is no coherence between scattering particles scattered from different target particle. Okay, so this will happen only if the particle size, the incident particle size is very small compared to the average distance between the incident particle, the average distance between the target particles. Okay, now the fifth assumption, the interaction potential depends only on the separation between the incident particle and the target. Okay, so there is again an assumption. Okay, so assume Assume the interaction potential depends only on the relative position of particle. It is V let R1, R2 are the position of the incident and target particle. The V of R1, R2 can be written as V modulus of R1 minus R2. Okay, so it depends only on just the separation between the incident particle and the target. Okay, so with these assumptions, we can directly start our problem of the scattering of spinless particle. Okay, so before begin with, we can have just the schematic diagram of our scattering. Okay, so this is our schematic diagram. So we have an incident particle, the scattering center, and the scattered particles. Okay, now in quantum mechanics, the state of the system is characterized by wave function. Okay, so we'll be using the wave function to represent the incident particle and scattered particles so on. Okay, so there are two particles. The incident particle location we can denote by symbol R1, and the scattered particle we can denote by symbol R2. Okay, then what would be the Schrodinger equation satisfied by this problem? So we have incident particle, the scattering center, and scattered particle, and so on. So in this entire problem, what would be the Schrodinger equation? So the Schrodinger equation would be a three-dimensional Schrodinger equation. Okay, now suppose the potential is static in time, then we can use the time independent Schrodinger equation. But it is not a single body problem. We have two particles, so it is a two body problem. So we can use time independent Schrodinger equation. Schrodinger equation for two body problem. Okay, so this equation will become minus h bar square by 2m1 del 1 square plus minus h bar square by 2m2 del 2 square plus the potential v r1 r2. Okay, and the total state I can represent as psi of r1 comma r2. That would be equal to the total energy, the psi of r1 comma r2. Okay, so this will be the detailed the time independence from the equation of this the scattering problem. Okay, now we are very fortunate to know about the reduced mass of the two body problem. That is, if you have a two body problem, then it is possible to convert a two body problem into a one body problem by using a reduced mass of the system. Okay. Now here, if you look at in the center of mass frame, we'll have two particles coming towards the center of mass. Suppose if the center of mass is here, and in the center of mass frame, what you can see is the incident particle would be moving towards the center of mass from left, and the scattering center would be. What would happen is when the incident particle moving towards right, the center of mass basically will shift towards right. Okay, so if you're looking from center of mass frame, then you can see that the incident particle is coming from left and the scattering center is coming from right side. Okay, Now it is a two body problem. Now it is possible to convert a two body problem into a one body problem. So it is possible to view a two body problem into a one body problem with the help of reduced mass mu 1 by m1 m2 divided by m1 plus m2. Okay, so with the introduction of the reduced mass, how would be, if it is a one body problem, how would be our the Schrodinger equation? Okay, so the Schrodinger equation can take the form minus h bar square by 2 mu del square plus v. Now, since potential depending only the separation between the particles, so v of modulus of r1 minus r2. Okay, so instead v of modulus of r1 minus r2, we can represent as v of r acting on psi of r gives e into psi of r. Now, usually the effect of scattering center is very limited because if the incident particle become very close to the scattering center, then only the interaction happens. So if the incident particle is very away from the scattering center, then there is no much interaction. So if typically, if the separation between r is large, or if the separation r is large, then the interaction potential would be almost zero. Okay, so for such cases, that is for r tends to infinity or for r very large, I can write the equation as minus h bar square by 2 mu del square psi of r is equal to e psi of r, or del square psi of r plus 2 mu by h bar square e psi of r becomes 0. Okay, now 2 mu e by h bar square I can write by symbol k square. So this can be written as del square plus k square psi of r equal to 0. Now, what are the possible solution for this Schrodinger equation? So there are two possible solutions for it. So one is the psi of r can take the form of some a into e raised to I k dot r, and the other possibility is psi of r is some a into e raised to I k dot r by r. Okay, so if you look at the first equation, it is like a plane wave, and the second solution look like a spherical wave. Okay, now we can go back to our original problem. So in the schematic diagram, you can see that this is my incident particle and this is a scattered particle. And if you look at uh, the wavefront of the incident particle, the wavefront of the incident particle will look like almost plane. Okay, we'll get a plane wave. Here the incident particle is a plane wave. And what about scattered particle? The scattered particle will almost look like a spherical wave. Okay, so almost it will be of spherical because it will be distributed over all angle. Okay, then we can see that there are two possible solutions for it. So this the first solution would be corresponding to the incident, and the second solution would be corresponding to the scattered. Okay, now since the k need not be same for the incident particle and scattered particle, if it is the elastic scattering, the k must be same. For inelastic scattering, it need not be same. So in general, I can write the incident particle, the wave function of the incident particle will take the form a raised to I k dot r. Okay, for the same time being, I put k0 now to represent the wave vector of the incident particle, and the scattering, we can write it is a e raised to I k dot r by r. Okay, now this is seen that the scattering is the spherically symmetric. Is at all angle the scattering wave function are same. It need not be true. Okay, so if there is no spherical symmetry, if there is no spherical symmetry for scattering, then what about this scattering wave function? Then the scattering wave function would depending upon angle theta and phi. Okay, then psi scattering would also be function of theta and phi, because at different angle you will get the different scattering cross section. So this I can write, so I have to include a new term here, so that I am including a term f of theta phi e raised to I k dot r by r. So this f of theta phi gives the angular connection for the scattering, and now this f of theta phi is called by the name the scattering amplitude. Okay. Now we are going to see what would be the differential scattering cross section if this is a case. Okay, we have got the wave function for the incident particle, and we have got the wave function of for the scattered particle in general. Okay, now it is easy to find the expression for the differential scattering cross section. Okay, now we can look at the differential scattering cross section. Okay, so by definition, d sigma by d omega is a function of theta and phi is 1 by j I n dn by d omega. Now, how to find this j? So, in order to find j, you can just recall the continuity equation. So, continuity equation gives the flux j and dou rho by dou t. So, del dot j plus dou rho by dou t must be 0. So, this is called uh, the local conservation of probability. Okay, now what was j here? So j take the form IH cross by 2m psi del psi star minus psi star del psi. Okay, since we know about the incident wave function, the incident wave function psi I n of r is simply a raised to I k dot r, and I can easily find out what would be my the incident flux. So incident flux will take the form IH cross by 2m a e raised to ik dot r. Now we have to find the gradient of psi star. So psi star would become a e raised to minus ik dot r, and if you differentiate it, it that would become, okay. So this is k0. It become minus I k0 into a star e raised to minus I k0 dot r. Okay, so that is your del psi star minus a star e raised to minus I k0 dot r multiplied by I k0 a e raised to I k0 dot r. Okay, so what would be the final expression here? So the final expression is very simple. It become h cross k0 by 2m into modulus of a square. Okay, so this is a k0 vector. So this you can do it yourself. Okay, you can try it down how to perform this till say star. Okay, we can use any one of the coordinate system to do that. Okay, so that's about the incident flux h cross k0 by 2m mod a square. Now what about the scattered flux? So that would be j scattering. So first of all, what would be our scattering wave function, which is a f of theta phi e raised to I k dot r by r. Now we can find out the j scattering is again by definition ih cross by 2m psi scattering del complex conjugate of psi scattering minus del psi scattering. Okay, so if you do this carefully, what we'll get it, we assume this scattering amplitude is a complex quantity. So this would become h cross k by m mod a square by r square modulus of f of theta phi square. Okay, so that's about j scattering. Okay, now so j scattering is basically a flux. It is the number of particle crossing unit area in unit time. Okay, now in order to find out d sigma, the difference scattering cross section, we should know about dn, the number of particle crossing the unit solid angle. So dn, okay, so dn you can find out is equal to j scattering into r square d omega. Okay, so if you look at a solid angle d omega, so how many particles are going through this in unit time? That is what is called dn. So if you find j scattering, so j scattering into this cross sectional area. Okay, so this cross sectional area I can denote by symbol dA. So j scattering into dA would give dn. What would be dA? This scattering cross section area, this area, this the area dA is simply r square d omega. Okay, so therefore dn would be h cross k by m mod a square mod f of theta square into d omega. So r square would cancel. Okay, next we can find out the expression for the differential scattering cross section d sigma by d omega, which is a function of theta and phi, and this is given by 1 by j I n dn by d omega. So what is j I n? So j I n we already got h cross k0 by m modulus of a square, and what is dn? H cross k by m mod a square mod square of f of theta phi divided by d omega. So this d omega would cancel. Okay, so m cancel, h cross cancels, mod a square cancels. So finally, this take the form a by a0 modulus of f of theta phi square. Okay, now since we have already assumed the scattering is elastic, then the wave vector for the incident particle and scattered particle would be the same. Okay, so the k and k0 would be same for the elastic scattering. For elastic scattering, k equal to k0. So therefore, the differential scattering cross section, which is a function of theta and phi, that is simply become modulus of f of theta phi square. Okay, so this differential scattering cross section is the mod square of scattering amplitude. So that is the final result. Okay, so differential scattering cross section is square of scattering amplitude. So once we know the scattering amplitude, and what is scattering amplitude, it gives the angular distribution of the scattered particles. So if you look at the scattering wave function, the scattering wave function take the form some normalization constant f of theta phi e raised to I k dot r by r. Okay, so this f of theta phi is called scattering amplitude. Okay, so in order to know about the differential scattering cross section, only we have to know about what is this scattering amplitude, so that the problem is solved. Okay, so we can stop it here. So in the next class, what we'll do is we'll find a procedure or a method to find the scattering amplitude of a problem. Okay, so we can just summarize what we have discussed today. So we have started with the scattering of spinless particles. So we are not considering the spin of the particle in this entire lecture. Okay, we are neglecting. We are not assuming the spin, not only for incident particle but also for the scattering centers. Okay, and there are other few assumptions also. That is, the scattering centers are very thin, and there is no coherence between the scattered particle, and there is no multiple scattering, and so on. And we also assume that the the interaction potential is independent on the direction between the direction of the incoming particle and the scattering center. Okay, so it just depends only on the separation between them, not on the direction. Okay, so with all these assumptions, we have made this theoretical picture of the problem. Okay, so if you look at the schematic diagram, the incident particle is look like a plane wave function, and scattered particle will almost like a spherical wave. Okay, now if you go for a detailed Schrodinger picture, it will be a two body problem, or is a Schrodinger equation for a two body problem, and time independent if you assume the potential is time independent. Okay, and since the solving of two body problem is a slightly difficult task, so we assume we will go for a one body problem. So if you're looking from the center of mass, this two body problem can be converted into one body problem with the help of the concept of reduced mass. Okay, now then if you're looking far away from the scattering center, the interaction potential will be almost zero, and your equation takes the form del square plus k square psi of r becomes zero, and there are two possible solutions for it. Okay, so if you are looking very far from this scattering center, there are two possibilities. One is you can have incident particle, and other possibilities you can have a scattered particle. So, so there are two possible solution. One solution look like the wave function for the incident particle. The other solution look like the wave function for the scattered particle. But for the scattered particle, there can be some angular dependence also. That is at different angle, the wave function may be different. So we have introduced a new quantity in order to give the angular connection to the scattered wave function, and that quantity is called a scattering amplitude. And finally, we have seen that the scattering amplitude is indeed a very important quantity, because the differential scattering cross section for elastic scattering will take the form of mod f of theta phi square. Okay, so different scattering cross section is simply the mod square of the scattering amplitude for elastic scattering. Okay, so next we look into how we can compute this the scattering amplitude for a particular problem. Okay, so thank you everyone for watching. So we'll see you in the next class.